Okay. So let me show you a couple of slides and use this for a couple of examples. So we have been describing systems mainly by the state model. And if you want to do a sketch of what is happening, we have some variables that you impose. Okay? These variables can be, for instance, the position of a valve, the degree of opening a valve, or a, a rate of administration of some drug to the system. So it's something, or an electrical value. So it's something that you can manipulate. So this is an input variable, input a manipulated variable. Okay. And then you have the system reacts, and you have something that you measure. That's the output measure, the output variable. Okay. And in between, what happens? We have the state model. We have the state model, and the state model is split in two parts. One is a set of differential equations that relates the state variables with the input. Up to now, we have considered examples in which we had no input, but I will give you some examples in a moment. And then you have to say, what is your model of measurement? For instance, you can measure one state variable, one of the state variables. You have three state variables, you measure all of them, or just one, number one, or number two, or number three, or whatever. Or you have a function of the state variables. Okay, you can have a nonlinear function of the state variables. So a system is somehow something, is an operator that transforms time functions into other time functions. Okay? But for this, we won't be exploring it for the moment. So let me give you some examples. And my example is the infection by HIV-1. Okay? So HIV, do you have an idea of how HIV-1 affects your body or the body of someone?
No idea.
No idea? José Basilio, I'm just seeing the top of your head. Can you lower it?
Sorry. Yeah, because I'm sorry. Because I'm seeing. Yeah, because I'm seeing. Yeah, I'm sorry. Because I'm seeing the presentation in the.
Yes,
the
yes,
bigger,
okay,
the bigger
okay,
screen, but the camera is in the laptop.
You're free to do it. You're free to do it.
Yeah.
But no one dies from HIV infection. What you die is from the consequences.
Yes.
Of being infected, because HIV acts at the level of your immunitary system. So your immunitary system has two types of cells, roughly speaking. Actually, it has many types, but you can group them roughly into two types of cells. Some cells say what is self to the body, that is to say, what is proper from the body, and discriminates it from something that is extraneous, that comes from the outside. Probably it's a menace if you have something coming from the outside. So you have this type of secret agents, and then you have warriors. And when you sign some particle which is not self to the body, you raise an alarm, and then the warriors come and neutralize it. Okay. Now, what does HIV-1 infection do? It mixes up. The secret agents, the security. Okay, so the security no longer recognizes foreign particles, virus or bacteria or whatever, in particular, so biological molecules. And worse than that, there is a moment in which HIV-1 changes the cells that do this work for the immunitary system in such a way that the immunitary system starts to recognize as non-self our own body. So the immunitary system turns against the body of the person. Okay, so let's see what happens. We will be concerned with a class of blood cells called lymphocytes. Okay, and you have several types of lymphocytes. In particular, you have the so-called T lymphocytes because they reach maturity passing through the thymus. Thymus is a gland that we have. Okay, and let me show you the structure of HIV-1. So you can see here, this is an electronic microscope picture, and this is a schematic view of a virus particle. So what do you have? You have a capsule, and you have these proteins GP41 and especially GP120, and these proteins allow the virus particle to attach to the walls of a cell in the human body and to enter it, to go through the walls of the cell. And what is inside the virus particle? You have a part of RNA. You are familiar with RNA and DNA, no? The helix of
Yes.
the nucleus of cells. So it has RNA, and it has a number of enzymes. Okay, you have 3 main enzymes. You have integrase, protease, and reverse transcriptase. And let's see what they do. So this thick line is the wall of the cell, and the virus approaches. It attaches to it connects to the cell, and it puts inside parts of RNA. And then with reverse transcriptase, the RNA is transformed into viral DNA. Okay, so this is why this virus is called a retrovirus, because it can generate DNA from RNA for small parts, and this was thought not to be possible for virus. And then you have a chain of DNA, and with the integrase, you insert this chain into the DNA of the cell. So at this moment, the cell, you know that activities of the cell are connected by its own DNA. So when you insert the DNA of the virus, the cell is no longer able to act correctly. And it starts producing, sorry, it was not, okay. It starts producing another a set of proteins and molecules that are then integrated by one of the enzymes, okay, and form new particles of virus, new virus particles. Okay, so in this cell, remember, this cell has a function of deciding whether something that it sees in the blood is something physiological, good to the body, part of the body, or outside from the body. And at this point, this cell from the immunitary system, the so-called T CD4 plus cell, is no longer able to do that. Okay. So how can we model these things? Probably I have here one picture in which you see the new virus particle being created and expelled from the cell. How can we model this thing? There are many models, some very complicated, but let's consider one of the simplest ones. And the ideas for the others is just consider more types of intermediate products or concentrations in some regions, but the principles are the same. So let's try to explain this very simple model. So I only have three variables. The number of LC T cells per unit volume, so usually per microliter. Then the number of infected cells and the number of virus particles. Okay? So what is the idea here? You produce some LC cells. Let's assume you produce it with a constant rate. Okay, and these cells they are eliminated because they die, and they also combine with free particles of virus. So this black dot means combination, and they produce infected cells that in turn produce more free virus. And the free virus, it's, well, you can't say they die because they are not alive. They are not living bodies, but they are somehow inactivated with some rate. And the infected cells also have some death rate that eliminates them. Okay, so this is a network of what is going on. And we write now equations making a balance of the different types of beings here. So the LC cells, infected cells, and virus particles. So the state equations are derivatives of these three quantities with respect to time. Okay, and take the healthy cells, so not infected cells, uninfected cells, they are produced in a healthy person. You only have these first two terms, S and minus dt. S is a constant rate of production. Okay? And minus dt is the death term. So S makes T grow. And this minus, if D is positive, T of course is positive, makes T decrease. So you have a balance. In the end, you will have a balance. Okay? I will discuss that in a moment. Now, you also have this term here. Forget about this term between brackets. So it's a negative term, and you assume that the reduction of healthy cells due to infection, so turning healthy cells into infected cells, is proportional to the number or to the product of the concentration of healthy cells and virus particles, which is reasonable. Okay? Actually, it's the simplest function that you can imagine that is able to mean this. Now, you can have a treatment. So you can give a drug, and the drug, I mean, you take your pill. What happens to the pill? The pill goes into your body, passes by your stomach, goes to the intestines, then takes some time to pass to the blood current. So one thing is the amount of drug that you are taking. In Portuguese, drug, remember, the word is fármaco, não é droga, right? Not my fármacos. And so you take some amount of drug, okay? And this drug will have some effect, okay? And the effect, you have a minimum effect, which is 0, and a maximum effect, which is the maximum effect in some units. You can normalize it between 0 and 1, or 0 and 100. Okay? In this case, this U1 is such that it varies between 0 and 1. So if you have no drug at all, no effect, then this grows. This term is free, this beta TV is free, to reduce the number of healthy cells, turning them into infected cells. So what disappears, the minus here, is exactly the same term, but with a plus here to increase the number of infected cells. Okay? And now, if you start taking drug, if you have the maximum effect, the maximum will be 1. So you may force this term to be 0. This is impossible. Okay, this is impossible in HIV. So you will have some value there. Now let me make a sketch. So stop sharing. So using the system language, you have the dose, okay? So this is the dose of medicine that you take. And then you have something which is a dynamical system that connects the those that you have taken to the concentration, the effect concentration. In this case, the effect concentration is the plasma concentration. Okay? And this is a linear system. This is the pharmacokinetic model. Okay. So, for instance, if you take some drug every day, you have something like this. Your function is something like this. Okay, this is time. 0 and then a kick. 0, 0, 0, 0, then a kick, and so on. Okay? And what happens? You will have something that grows due to the kick, then decreases. Then again you have the kick, then it decreases. Then again you have the kick and it decreases, and so on. Okay, so these are the times in which you have the kick. These times typically is what happens. Okay, later we will see how to model this stuff, but intuitively I think that you can accept that stuff. Now, one thing is the amount of drug, that the concentration of the drug that you have in your blood. The other thing is the effect. So you need something and here, let's call it U. You have the drug effect. And here you have the drug concentration. At a place where it does some effect, okay? And this is typically between 0 and 1, okay? So you can usually model this by some static nonlinearity. This is the pharmacodynamical model, PD. And usually you have something that says that if this is C and this is U, this is the maximum effect, let's call it 1. You can multiply by some function and you will have something which is, take a lot of drug and you approach that, okay? Typically, you can say that you can use an exponential. I mean, you could say, I could write the biochemical equations for this, making best balance between the molecules. It's very complicated. It's virtually impossible. So what they do is they approximate this by some a priori function. For instance, it could be U. It's some U max, some constant. And then you have C, a constant. Okay? So if C is 0, then this gives you 0. Then if C is very big, C is much bigger than C50, then this is approximately C divided by C, so this approach is 1. If C is equal to C50, what is the value? If you have here C equal to C50, this value of C is what? You get
maximum value divided by 2, 0.5.
That's right. Okay. You can also put here some some exponent that can be a fraction. Okay? And then you do observations and you try to compute the parameters are alpha and C50. Okay, you try to play with this so that the data that you observe correspond to the patient that you have. Now, one difficulty is that these coefficients vary with a person, and sometimes in the same person they vary in time. That's what very big difficulty in all modeling of physiological systems in this way. Okay, so you have this, and then you have the equations I wrote, and you have T star, and U. And then you have sensors, okay? So this is the state model that I'm studying. Made of 3 differential equations, but you don't measure this. Usually what you measure is the sum of T and T star, the total number of cells, or the total number of cells and the number of virus particles. This is a V, and this is a V. The number of virus particles, you measure this, and then total number of cells. It's very difficult to do measurements. Okay? And we are speaking about here about this model. But I told you all this story. You will see in a lot of papers, sometimes people don't have an idea of what they are speaking about. Usually you assume that you manipulate directly this effect. But they usually, when they write the papers, they call the effect the dose of drug dosing. Okay, so this is milligrams per time, per second, per day. So it's mass per time or volume per time. Okay, usually in HIV-1 is mass per time, the amount. Okay, so we are just concentrating here. We are concentrating in this part here. And don't forget then that then you have your sensors. And what you measure, usually measure the sum T plus T star and phi. And it, as I told you, it's very, very difficult. Later, I will make some considerations about it and the rate of sampling in particular. Okay, any question? So if you want to model, some treatment, you always have the dose, so the flux into the body of the treatment. Then you have the pharmacokinetic model. This is a linear model, and you have that relates the drug that you are taking, unit per time. This can be in the form of pills, but in some other cases, not HIV-1, you can have something which is a continuous function. And sometimes it's a continuous function. For instance, in anesthesia, you can give a bolus, that is to say an injection, or you can have an automatic searing connected to a computer with MATLAB, and you are imposing a constant dosing. You are always injecting something. okay? To give you an idea, these small pumps in anesthesia, you are speaking of flows of, say, the maximum 20 milliliters per hour. So it's a droplet. It's something very tiny that goes into the body. Okay? Later, we are going to study this model, at least in general terms. I mean, you could write a book just on PK models. And then you have this pharmacodynamic that transforms the effect concentration on something that we measure. It's the effect of the cell. Okay. Then you could also consider things like toxicity, measure toxicity, and the development of resistance. Okay. Usually, resistance is something that affects this C50 parameter, depending on the drug concentration dropping below some value. Everybody here knows when you are healed from your throat and you have to take some antibiotics. Okay, you have to take it every day or every 8 hours or every 12 hours. Otherwise, what happens? The virus changes, develops a resistance. Okay, so when it goes below some value, what happens is that the C50 grows, and to achieve the same amount of effect, you have same amount of effect. If you don't take it, then you need to reach this half effect. You require a much bigger dose. Okay, so you can easily manipulate. You can easily model drug resistance by having algorithms to manipulate C50 as a function of the concentration effect. Okay, so let's go back to this dynamics of the cells. Any question about this?
No.
So, actually, there is another thing that I want to discuss with you. Can I clear this?
Yes.
Okay.
Yes.
So, remember the first equation. The first equation was dt equals to S minus d. Remember that this is the symbol for a derivative and this is a coefficient. Minus ds minus, and then we had 1 minus u1 beta t v. Okay. Now, suppose that our patient is not infected. So this V0, and you don't have it here. So let's clean it. Okay. And suppose that you have no T cells. Okay, if you have no T cells, you will die because all infections will attack you. Okay, but suppose that you have no T cells, or you have a very small, okay, 0 T cells. So this is T, and we have time here. Okay, so I want to look at this differential equation. It's a good exercise. So if you have 0 T cells, what happens initially? What happens to the derivative? What happens to t? S. Oh, sorry. This is not S, this is T. Okay. So S and D are constants. So initially you have T equal to 0. Okay. So here you have T equal to 0. What happens to the derivative?
It's equal to S.
It becomes equal to S. So the derivative is S. So where is T going to be? Up, down, stays the same?
It increases.
It increases because the derivative is positive. Is it okay, Jose and Cave?
Yeah.
Okay.
Yes.
So you start growing. Time passes and you start growing. When you start growing, what happens? Let's make a slower rate. So you start growing. And now, are you going to continue like this? Are you going to do like this? Not behind, but faster and faster and faster? Or are you going to do something like this? What you say? So we have A, we have B, and we have C. So goes always at the rate which is S, or go at a faster rate, faster and faster and faster, or go at a slower and slower and slower. Look at the equation. What happens to the rate of growth? Remember, is the derivative.
As we have more T cells, we will have a slower increase. So
As we have more T cells, what happens?
that
What happens to
term
this term
increases.
here? It's a negative term. So, Maxi,
Yes,
what happens when you increase T?
dt increases, and since we are,
You
it
see,
has
you
a
say that
negative.
dt increases.
No, it goes down
The-
because it's
the-
negative.
Yes.
No,
Yes,
I was saying d times t. The
Oh, d
term,
times t
yeah,
increases. Okay,
exactly.
okay, that's right. And so the derivative, what happens to the derivative?
It is smaller than what we had before, so
Okay, so A, B, or C?
I would say c.
So Maxi says C. Jose,
No, I also think it's C because you will reach a plateau because you will not have more T cells.
but Cave is very optimistic, much more optimistic. So we prefer things that go faster and faster. So what you select, A, B, or C?
Oh yeah, I think also this C, yeah.
C. Okay, that's right. Because you are reducing, T is always increasing, is always positive, so and increasing. So this stuff here will go slower and slower and slower. Okay.
Although I think that in a lot of biological processes, so what we see is always the C curve, because it always increases in the beginning where you have a rather linear phase in the beginning, but it tends always to reach a plateau.
Okay.
No?
Remember the story of the logistic equation that models that? This is a linear one, but with a constant term. Okay. So in particular, so this is a linear model. We have seen that it's true, Jose, what you're saying. This model, it's true. So let's clean what is not, should not be. So this is not, and we all agree. We all agree that it does something, it reaches some plateau. Okay, so it's approaching something. Okay, now what I was saying is that this is a linear model. We have seen a similar behavior with a nonlinear model given by the logistic equation. Look at the slides behind. Okay, but that's it. That's another story. So can you compute this plateau? If you started at the value of the plateau, what would happen?
We would stay there.
It would stay there. So for what value of t, you stay there?
This seems so much the Michaelis-Menten.
Michaelis-Menten is
For enzymes, I know, but
it's nonlinear. And it's a rate of growth. Okay, here the rate of growth, I mean, is given by this. Actually, it's not constant because it varies with t. What is the value of t such that if you start there, you stay there? It does not change.
S divided by d.
S divided by this, by d. So if t of 0, if t of 0 is S divided by d, so what happens? What is the value of the derivative?
0.
Is 0, because if you place it here, then the derivative will be 0. So you will stay here. Okay, just solve this equation. Oh, they never cross. So solve this equation, dt equal to 0. This means that S minus dt is equal to 0. Sorry, minus d t is equal to 0. And so you get that. Okay, everybody agrees? What about if you start here? What about if you start here? What happens? So t, the derivative is what? Positive or negative?
Negative.
It's negative because in this interval it's positive. If you start here, for instance, it does something like this. But if you start here, the derivative is negative and it goes like this, okay? So my point here was look at the derivative and think. We haven't solved this equation, okay?
Yeah.
Give some values to S and D and simulate it in Simulink just to convince that it is like this. But without solving it, we could just using the sign of the derivative find an idea about the solution. Okay? Don't you think this is amazing? I think I do. Okay, well, let's go back. Let's go back to our model and to the slides. So this is the model of an healthy person without this term, this exotherm. Then you have this exotherm that makes the T grows smaller. Okay? Now, the number of infected cells is the term that decreases in the healthy cells, you increase it in the healthy cells, in the infected cells. And you have some rate corresponding to the death of the virus. So it's sometimes they call this mu2, the rate of mortality of the virus, but it's, you can't say it's a rate of mortality because viruses don't die, they are inactivated somehow. Okay. Oh yes, this is a rate of mortality not of the virus, but of the infected cells. So this is really a rate of mortality, like the D. So mu2 is like the D there. And now you have the virus, and the virus is proportional to the number of infected cells. Remember that infected cells produce virus. So the more infected cells you have, the bigger is the rate of production of virus. So you have some constant of proportionality times the concentration of infected cells. And here you have another medicine, you have another drug. Okay, this is the effect of the second drug.
I'm sorry, I can't
Yeah,
see the
me too.
slides.
I was going to say this.
Sorry, you can't see it. Oh,
Yeah,
okay.
yeah. But
But
the
you
thing
can,
is,
so you
and
can
Maxine
imagine, you can imagine it, but you can't see it. That's
Yes.
very good.
But
Sorry.
Maxi, you were so focused that I thought I was
No,
the
I
only one
was
who could not see
waiting.
it. Thought, okay, maybe that's my connection problem. I should check it.
That's a very good point. We can't see anything. Okay.
Yes. Okay, so
I
yes,
could answer, but how can you see it? It's
now we
obvious.
see. Now we see.
Okay, so what I was saying is that so what is appears from the first equation will appear in the infected cells. Okay, so the number of cells that decrease in the healthy cells due to the interaction with the virus is the same number of cells that become infected. So it's the derivative of the infected cells, T star, is proportional to this beta TV. Okay, and then this is the mortality term. This is the mortality term of the infected cells. Mu2 is the mortality rate. You multiply it by the number of cells, you have the rate of cells, of infected cells that die. And the last equation is the equation for the concentration of the virus particles. Okay, so it's proportional to the number of infected cells. The more infected cells you have, more virus you are producing per unit time. And you have another drug with effect U2, okay, inhibits the formation of new virus particles. So remember that the infected DNA of the cell started producing a number of pieces of RNA and proteins and enzymes. And then there is an enzyme that puts everything into a virus particle. And these drugs inhibit this action here. Okay? So the first drugs, the drug number one, inhibit this entering of the virus into the virus RNA into the cell. Okay, and you could also consider another drug. Actually, it exists that inhibits the integration of viral DNA into the DNA of the cell, into cell DNA. So integrase inhibitor. Okay, but we are, in our model we are just considering two drugs. One inhibits this entering, and the other inhibits this assembly. Okay, that's drugs number one and number two.
I'm sorry to interrupt, but I have to go fast to the toilet. I come right back.
Okay. I think that Jose is coming back. So let's wait for a few minutes to see if he comes back.
Okay.
Do you have any questions up to now?
No.
No, actually.
Okay, so we have a number of things to say. One is, what does this give you? I mean, if you put some numbers, what are the parameters here? S, D, beta, mu2, mu1, and k. If you give some values to these parameters, what happens? Okay, if you do a simulation, that's one issue. The other issue, other issues, questions about this model. Are you able to place questions about this model? Here is that. We were discussing to see what can we take out from this model. So this model, in this model, you have two inputs, U1 and U2. Remember the block diagram, very simple, that I placed at the beginning with the inputs. The system is a square, and then you have the outputs. So you have the input is U1 and U2. They are time functions. Okay, so these time functions, usually it's a doctor that tells you, well, take this pill every day, for instance. Okay, so it's a time function. And then you have T, T star, and V. So let me show you, these slides have what I just told you. So if you do a simulation, you get typically this type of result. Suppose that you start with 1,000 T cells per microliter, and no infected cells, but then you receive a small number of virus. Okay? And if you simulate this model, what happens? You get this behavior. So this is a simulation. The time is in days. So this is a little less than 2 years. And the number of virus copies grows very fast and then decreases. Okay? And the number of the cells decreases, and also the infected cells go very fast and then decreases. Okay? So during this period here, the infected person, it's about, say, 3 weeks. It's like having a flu. You have a flu or influenza, you have some fever, but then something happened. What happened? What do you think is a bad thing, a very bad thing that happens here, that you see that has happened in relation to the organism of the infected person?
It will like increase constantly, so it will be like this. It will be the worst case.
What increases constantly?
So the like the infectious value. Am I right?
The infected?
Like, yeah.
Infected? It
Yeah.
increases, yes, but then it decreases again.
Oh.
No,
That's
I think the worst is the volume of T cells doesn't recover to the initial.
That's right. Now your immunitary system is much weaker than before. Okay, because you started having 1,000 T cells per microliter, and now you only have about, say, 200 or something like that. Okay, so your immunitary system became weakened, tremendously weakened. Okay,
Yeah.
what happens? The person can go on for between 2 and 10 years like this, and then by reasons that are not completely clear, the number of virus grows, the number of infected cells start growing, and the T cells go to zero, and the person develops AIDS and dies due to infection, say tuberculosis or something. These opportunistic infections that affect the patient due to the fact that his immunitary system is not working. Okay, but this last effect is not considering the model. So the model only models the initial part. Okay.
But but nowadays, there is this antiretroviral
That's right. So
drugs.
this is an untreated person. If you apply treatment, you will be able to raise this value up.
Yeah, because nowadays I have the feeling that the immune suppressive syndrome is like a chronic disease.
Yes, you can. A person can live for 20 years having an almost normal life. Okay, but needs the treatment.
Yeah, of course, and it's really expensive. Really
The
expensive.
untreated. If you want to, you can simulate. You can simulate. You can simulate the treatment here. Okay, you can simulate the treatment here, and you see that you start applying the treatment here after 150 days, and you bring your virus concentrations to, you can show that it will never go to zero. So you need always to take the drugs. If you stop taking the drugs, what happens is that you have a kind of spring effect. Okay, you have a kind of spring effect. So it grows to a value which is bigger than what you had before. So you can study with this model things like using just one drug or both or two drugs. Okay, so two combined drugs. It's the dashed line, which is a little bit better. And one thing which is not modeled here is that you can have different galenic formulations. So when you take a drug, there is one part which is the so-called active principle, and the rest is something that gives volume. But this is very important because it decides factors like the time that the drug takes to make an effect and so on. So usually, despite having just in the beginning, there were just two active principles, but the infected person was taking, the patient was taking a cocktail of drugs every day. So you can use these models to model this stuff, okay? Now, if you look at this plot, maybe there is something that you would like to compute. Of course, you have the response here, but there is one thing that you would like to compute. No? The equilibrium point. In particular, how many equilibrium points? How many equilibrium points? And what are the equilibrium points? Could it happen that you have only one equilibrium point in this system?
What you mean one
equilibrium point. You have these equations. How do How do you compute equilibrium points?
You set the derivative to
Mathematically, I
0.
mean. You set the equations to the derivatives to 0. So you get the first equation to 0, the second to 0, and the third to 0. You have you know the parameters, okay? And you went down. Let's suppose that u1 and u2 are 0. So these terms between brackets disappear because you only have one. And how many solutions do this system have? Of course, you can compute them by pencil and paper, but how many could we have just one equilibrium point?
You mean for all of them?
I mean, one solution for these equations. When you equate this to 0, could you have how many equilibrium points do we have? Can we have? Well, it's the solution of the equations equal to 0. These are non-linear. These equations are non-linear, so you can have several values of t star, and v that makes the derivatives to vanish. Now, my question is, can we say that we have more than one possible equilibrium or no? Can we say that we have more than one possible solution or no?
I would say yes, because we can have a patient that doesn't have the virus. So
okay, the healthy person. So in the healthy person, what is the equilibrium? It's very simple.
So T star and V would be 0.
Okay,
and the healthy T cells,
Would be equal to 1.
you say t equal to 1?
Because all of them will be always healthy.
If you say, suppose that T star and V are 0, okay?
Yeah.
So if T star and V are 0, this term vanishes, so this derivative is obviously 0, also here. So let's look at the first equation. V is 0, this is not there. So what you get, dt is s minus dt. So what is the value of t that makes this to vanish? We have solved it 10 minutes ago. It's t equal to s divided by d, not 1. Okay, equate the derivative to 0. Okay, so there is one equilibrium, which is the healthy person. So t star equal to 0, v equal to 0, and t equal to s divided by d. Now, is there another equilibrium? Look now at the simulation. Is there another equilibrium? At least another one?
Yes, after a person is infected by the virus.
Apparently, it goes to an equilibrium.
Yeah.
Okay. Now, we have these two equilibrium. Actually, there are no more. It's just these two. If you write equations and so on, and solve them. Now, what about stability? What do you think? Let's start by considering the healthy person. The healthy person, you have t star equal to 0, v equal to 0, and t equals to s divided by d. Is this a stable equilibrium? Remember what means stability. Stability means that if you start at equilibrium, you stay there. But if you deviate just a little bit,
it
you
will
move
go
away.
Is
it stable or unstable?
It is stable.
Stable. Because if you go to, if you look at the ancient knowledge of the Orient, no, Buddha, life is something stable, isn't it? Hey, Max, do you know anything about this? Probably not. You
No.
don't look to know very much about the ancient philosophies of the Orient. But it sounds reasonable to say life is a stable thing.
Well, that's
So, but that's a philosophical point of view. Here we have a mathematical point of view, and sometimes mathematics is critically different from philosophy. Okay. So if you are, what does it mean that the Gauss state is stable? It's a question. Stability means that you have the equilibrium at this point. Now deviate it a little bit. If it is stable, it stays around, or even it returns to the equilibrium, close to the equilibrium. If it is unstable, you deviate it a little bit, and goes away. So
if we are in equilibrium and we decrease the number of T cells for some reason,
what
T will
happens?
be smaller than S divided by D. So that value of the derivative will be positive, and
You
it
grow
will again increase. And yes,
So T, at least T has some stability, but you have other variables. What happens if you place there 2 or 3 virus in the body? What happens? What does your intuition tell you? I mean, if you have a few variables, a few virus, okay, what happens is that virus will multiplicate,
and infect the cells.
and you are no longer healthy. That is clear from the way the virus progresses. Okay, we don't have, for the moment, we don't have yet a mathematical tool to study stability, but you accept that if you do the perturbation that consists of adding just a few virus particles, okay, then you will move away from the equilibrium of the healthy system, because T star and V will go where? Will go where? Look, let's look at the simulation. We'll go to this other equilibrium. What about this other equilibrium? Is it stable or unstable?
the equilibrium about the number of copies.
When you have the infection went for a lot of time. So you go here to this point. So it's T equal to this value, T star equal to this value, and V equals to this value. Is it stable or unstable?
Probably it will, if we add more virus particles, it will go up again and then return to the.
Actually, it's pretty much stable, because you have approached it. If it was not, if it was unstable, due, for instance, to, sorry, this is unstable. If due to instance to numerical errors, you would not reach this point. It would go to somewhere else.
Okay.
Okay. So maybe you haven't learned anything about mathematics for biology, but now I've shaken your beliefs that else state is a stable thing. No, it's unstable. And illness is an unstable thing. No, it's stable. That's the problem. Okay. Now, in mathematical terms, we need a tool. We don't have it yet. We don't have it yet, but at least we could discuss this. We have seen how to model a reality like an infection by virus. And we have seen this story. We have multiple isolated equilibrium points. That's something that can happen. You can have even more equilibrium points. In this case, we have 2. Okay. I don't dare saying this in English because it's too complicated, but there is a joke that says that a saúde é estado transitório que não augura nada de bom. Okay, so the healthy state is something is a transient state for which the prognostic is very, very bad. Okay, because you are going to become ill. Okay, so I think this was okay. This has some details that I will go away.
So you mean, so this means that when you're healthy, one should expect that one becomes sick.
That's
but
right.
once you're sick, you cannot expect to be healthy again. Is that
But
correct?
then you have control. Control in this case is applying is medicine.
Yeah, then you have a
that
feedback.
drives you,
Yeah,
keeps
then
you.
you have
Control is able to counteract this instability.
yeah,
Very
because even
much like when you have a pendulum. Okay, when you have a pendulum, this upwards position is unstable, but you can equilibrate it using a controller. Okay, that's the power of control.
although biologically we could be here for hours discussing what is disease and what is healthy, because for example when we have an infection or a contamination, it's part of a healthy individual to fight against this infection. You understand what I mean?
You have a number of feedback loops inside.
Exactly.
Okay.
Only when these feedback loops somehow stop working is then you become sick, but really sick in the sense of a chronic disease of some sort.
Okay.
So if like the inflammatory process is a physiological process.
That's right. That's right. That's right. You are counteracting. You are defending the organism up to some extent.
Yeah.
Up to what is possible. Then you have another thing, which is actually we have a lot of feedback loops. I mean,
Yeah, exactly.
Here I was considering an extraneous or exogenous, better to say, an exogenous variable. But in the organism, you have a number of feedback loops. So you can think of this system as a physiological system, as separate systems that interact, and they interact depending on, in particular, feedback. Feedback is something which is fantastic, and it's someone engineered this to keep the temperature the correct point and so on, to make you grow in the correct way and so on. Okay, but yes, I agree with you that we could be discussing hours, but sometimes when one discusses hours, it's about generalities. I would like you to make you learn some specific techniques. This story of the derivative and the state model is something that if you manage it, then you will have much stronger arguments to, if you write equations and then you analyze the equations using simple arguments, but completely logical. Okay? And I placed here our main tool, the state model. Okay? So if you are able to write equations as you have a number of state variables, x1 up to xn, and the derivatives of each of these variables is equal to some function of the states, perhaps of exogenous variables. Okay, and if you have the body, then you can have part part is one state model, then you have another model that generates U. Okay, so you can couple them, the different subsystems. And you also have outputs, which is now made of algebraic equations. You don't see any derivatives here. Okay? The simplest thing is to say that y1 is x1, y2 is x2, and so on. But in many cases, you have some nonlinearity. So this is our description of nature. It does not describe everything. There are phenomena that are not well described in this way, but it describes a lot of things. And it's an important model. And what I'm going to do is first consider the case in which these functions are linear. So you have a linear combination of the state variables. What can we say about it? In that case, we can say a lot of things. And then consider the nonlinear case. And use the linear case as linearized versions around the different equilibria and patch. You see, patching. When you have some tissue and you have a hole and you patch something there and then you patch something here and there and so on. So you have different patches. You understand patches? Okay, in Portuguese. And using this technique of patching linear systems, you get an analysis for the nonlinear system, which again does not cover everything, but it covers a lot. So that's a program now. So to study properties first for a linear case and then for a nonlinear case. So this stuff that you can write in this way, in a compact way, using f is a vector, x is a vector, u and y probably are vectors. Okay? We will devote most of the time to this equation because this is very simple. Okay? Any question?
No.
So today we stop here. It's very important that you do the first series because you need to struggle with the differential equations and write the differential equations. And these series are about entering the world of differential equations. Okay. So the next lecture will be at 5:30 on Wednesday, isn't it?
Okay.
Yes.
Yes.
Okay. So now I will stop recording and